This episode follows the last air treatments videos for the tool changer build. In these videos, I'll outline the filtration systems and discuss the functions I might implement. Hi, welcome to Slow Engineering. I'm David. Let's review the plan for the filtration system. This system is designed to remove harmful fumes and particulate matter, and address fume leakage from the unavoidable gaps in the printer. Unlike most filtration systems that exhaust air outside the printer, I have also considered incorporating a circulation system that maintains a stable, warm environment within the chamber. The last time I discussed HEPA filters, I examined the HEPA filters from a robot vacuum cleaner and consider using it as my filtration solution. Through my research, I discovered that HEPA filters come in various grades to determine their filtration capabilities. According to Wikipedia, HEPA filters range between HEPA and ALPA filters. One tricky aspect is that some sellers market them products as H11 or H12 HEPA filters. Even more concerning, many filters sold online do not show any grades on their product pages. Filters classified as H11 or H12 do not effectively filter out the particulate matters generated by 3D printing. As a result, I began searching for a new source that provides filters made from at least H13 grade material. The sequence of the filters is the same as mentioned in the previous video. The HEPA filters goes first, followed by the activated carbon filter. I'm unsure how long a regular thin layer of activated carbon filters on air purifiers lasts in a 3D printing environment with ABS or ASA. Still, I can replace a cheaper coconut shell or column-shaped activated carbons more frequently. Additionally, I will implement a prefilter before the HEPA filter to reduce the large particles that reach the HEPA filter. This prefilter consists of two 3D printed parts with magnets on the edges sandwiched with a filter material. The fiber materials can be replaced often, while the frame can be washed. The housing is designed to accommodate the H13 HEPA filter, which fits inside and is covered by the prefilter. Activated carbons captures the VOCs produced during printing. However, it degrades quickly, especially when printing materials like ABS and ASA. To address this, I designed separate swattable cartridges for each type of filter. Additionally, I included a finer mesh at the bottom to trap the granular activated carbon. The carbon cartridges has a volume of about 600 milliliters, effectively capturing a decent amount of harmful VOCs. The next layer beneath the activated carbon filter is another filter, the same type as the pre-filters used before the HEPA filter. This filter is specifically designed to catch carbon powders and prevent it from entering the fan. The cartridge has a tapered shape that gradually decreases the cross-sectional area to match the fan inlet. This design helps to create a more even pressure distribution and reduces noise compared to a filter that immediately matches the shape of the fan inlet. I applied the same methods to the tapered shape at the inlet of the filtration system. These geometries create a pressure drop in the filter sections and slow the airspeed in the cartridge sections. A slower air velocity in the activated carbon sections enhances the chance of capturing VOCs. Gradually enlarging and narrowing the cross-sectional area allows smoother airflow, preventing turbulence. For monitoring purposes, I plan to implement both pressures and VOC sensors. There will be two pairs of sensors, one set at the inlet of the filtration systems and the other set at the outlet. The pressure sensors will be placed specifically to monitor the HEPA filters at a predetermined fan speed. A noticeable pressure drop after extended use indicates the filters may be clogged. The VOC sensor is more straightforward. If the outlet sensor displays a high index value, it signifies that the activated carbon has degraded and needs to be replaced. I use a 35mm in a diameter vacuum tube, which can be clamped at the filtration system's inlet and outlet. On the printer side, I only need to create 2 holes and use 2 adapters to mount the tubes onto the panels. This setup circulates air back into the enclosure, helping maintain a consistent temperature. These are the initial design concepts for the filtration system. The system's suctions create negative pressures within the enclosure, effectively containing the fumes and gradually purifying the air inside. A circulation mechanism helps maintain the chamber's temperature. While the filtering process might seem slow, I plan to use an additional exhaust fan to expel all the air from the chamber outdoors once printing is complete. This way, the fumes remain contained during the printing process. The system is currently under development, and I welcome any ideas or features you would like to suggest. Feel free to share your thoughts in the comments. As always, moving forward.